Hey guys, welcome to Safi Mixed. In this video, I'll talk about the different differential forms and integral form of Newton's second law. At the end, you will see that the integral form gives rise to another very important quantity. And the different differential forms of Newton's second law are important from different perspectives dealing with different theoretical situations. So to this end, I consider a particle in the form of a sphere and let the mass of the particle is m, and different forces, I call them F1, F2, F3 and so on up to Fn. These are the different forces acting on the particle. And when I'm representing the forces with vectors like this, that means I know about the direction and magnitudes of these forces. And when I know the directions and magnitudes of the forces acting upon a body, I can find the resultant force by vector sum, or I can write the net force F in the form of F1 plus F2 plus up to Fn, or I can write this in the abstract form like this: I runs from 1 to n f sub I. So this is a vector sum, keep that in mind, and I presume that you know about the vector sum. Now, once we know the force, we can write Newton's second law in its general form in the form F equals somewhere I1 to n Fi equals dp over dt. I call this equation 1. Here P is momentum of the particle, and we know momentum from the definition that it is in fact the product of mass time velocity. So if I differentiate this, I get dp over dt equals d over dt mv, and using the product formula for derivative, I can write this as m dot v plus m v dot, where m dot stands for derivative of mass with respect to time and v dot derivative of velocity with respect to time. That is, m dot is d over dt and v dot is dv over dt. Since we are considering a single particle and we presume that the mass of the particle is conserved, that is, it is not changing with time, under this condition I can set this part of the equation equal to 0 and can write this thing equal to mv dot. And if I substitute for dp over dt equals mv dot in equation 1, I can reduce the equation to this form, m times dv over dt, or in the formal form I can write this as dv over dt is in fact acceleration, therefore I write this as m times a, which is the case of Newton's second law for particles with constant mass. Now I can write this equation into components form by writing f sub x unit vector I plus f sub y unit vector j plus f sub z unit vector k, and on this side I can write acceleration in its components form, write it like this: ayj plus azk. Okay, I can obtain the dynamics of every coordinates by projecting this equation to the same axis. For example, if I take the scalar product or dot product of unit vector I with this equation, I can write this as I dot fx I plus fyj plus fz unit vector k equals m times unit vector I dot ax I plus ayj az k. And now using the orthogonality condition on the unit vectors, here I have to put a dot. I dot I equals 1, so I'm left with f of x, and I dot j equals 0, this term goes to 0, I dot k equals 0, this term goes to 0. From this side I just get f sub x, and from this side I dot I again equals 1, so I'm left with ax, and the rest two are 0, so that goes to 0. So this equation reduces to m times ax. And similarly, if I take the scalar product of j, that is, instead of I replace this with j and this one with j, then j dot I is 0, and I'll get fy from this side, and from this side I'll obtain ay. So I'll be able to write this equation, fy is equal to m ay. And similarly, if I replace j with k, unit vector k at this side and unit vector k at this side, then I get fz, and these two goes to 0 because k dot I and k dot j goes to 0, and k dot k equals 1. So then I get here fz, and from this side I get az, I get m dot az. And if I want to write this in differential form, I just remove these things and can write f sub x in the form m times d squared x over dt squared, because acceleration is the second derivative of position, therefore the acceleration along x-axis is the second derivative of x coordinate. And similarly, I'll be able to write the second one. Let me write that over here. Fy would be equal to m d squared y over dt squared, and fz becomes d squared z over dt squared. Okay, I call this equation 2a, this 2b, and this one 2c. Now, these equations gives the differential forms of Newton's second law for the three components of Cartesian coordinate axis. And if we know about the components of the acceleration from these three equations, we can find the magnitude of the corresponding components of force. And then using directional cosines, we can find the direction of the force. So if we know about the components of the acceleration, we can find the force. On the other hand, if we know about the components of force, we can find the components of acceleration. And then using the equation of motion, we can find the components of velocity and then the component of position vector. So we are then able to solve any problem if we know these things. On the other hand, let me remove first this. I consider equation 2a, this one, and I want to put the acceleration and the second derivative of position into another form. I can write d squared x over dt squared equals d over dt times dx over dt. And now dx over dt is in fact velocity along x-axis, so I can write this as d over dt into vxr, and the normal form I can write is a dvx over dt. So if I replace this value for this second derivative in equation 2a, I can rewrite the x component of force in the form of dvx over dt. And similarly, I can write for this one equation and for this one equation, and they will give me these two equations: if y equals m dvy over dt, and if z would be equal m dvz over dt. I call this equation 3a, this one equation 3b, and this one equation 3c. Now, again, this is the same things but written in different format. This is now first derivative of velocity, and that one, and these equations are written in the second derivatives of position, or the component of position, or of the coordinates. And similarly, I can rewrite this thing into another form, and I want to write that over here. That is, I can write dvx over dt in the form dvx over dx multiplied with dx over dt. Remember, I can cancel direct dx with dx to drop the equation back to this form. And this I can write dvx over dx, and this thing dx over dt is velocity along x-axis, so I write that at vx. In other words, I can write this as vx dvx over dx. Now, if I replace this value for dvx over dt in this equation, then the x component of force can be rewritten in the form f sub x equals m times v sub x dvx over dx. And if I repeat the same procedure for dvy over dt, then I'll be able to reduce the y component into this form: m v sub y dv sub y over dy. And similarly for the z component, I can write m vz dvz over dz. I call this equation 4a, this equation 4b, and this equation 4c. Now, the set of three equations 4a, 4b, 4c is another differential form of Newton's second law. So the equation 2, equation 3, and equation 4 are the three different differential forms of Newton's second law. They are equivalent, means whichever differential form you may use, you will get the same result, but they are presented in different ways. Here, it is the second derivative of position with respect to time, the first derivative of velocity with respect to time, but here we see the first derivative of velocity with respect to position. So the different forms, so they are called the different differential forms of Newton's second law. We can write another differential form by, if I rub these equation out, I can similarly break down this equation into the form fxi plus fyj plus fzk equals dp sub x over dt I plus dp sub y over dt j plus dp sub z over dt k. And from this equation, projecting the equation first to the x component that is taking the dot product of unit vector I with this equation would give me f of x equals dpx over dt, and similarly I'll get f of y equals dpy over dt, and for the third component I'll get fz equals dpz over dt. So this is another differential form of Newton's second law. Now, let me play with one of these equations. I can rewrite this equation in the form dpx equals f sub x into dt. And I can integrate this equation if I know about the initial conditions. Let the initial condition be that the initial momentum along x-axis is p sub ix, and the final momentum is p sub fx at times t naught in tf. Then I can integrate this equation formally to write this in the form integral p ix to p f sub x dpx equals integral from t naught to, or let me write this as ti to tf into fx dt. I can formally integrate this to write the result in the form of p sub x from pix to pfx equals integral ti to tf fx dt. Now, I cannot integrate this side so far as I'm not sure about the exact form of the force. And from this side, I can write, let me rub this out now. I can substitute the limits to write this as pfx minus pix equals integral from ti to tf f sub x dt. Or I can write pfx is equal to pix plus integral ti to tf f sub x dt. This quantity on the right side of the equation is very interesting quantity, and this is called impulse. And the momentum arising from this, because overall this is momentum, because we are adding this to momentum, so this would be momentum. And the momentum arising from this part is called impulsive force, not momentum. So this is called impulse, and this is very interesting quantity. The use of this quantity is very beneficial, particularly in cases where the momentum changes very abruptly, like in the case of collisions of particles. But I'll say more about that in another video. Nevertheless, this form, or in general this form of the equation is called integral form of Newton's second law. So the integral form of Newton's second law gives rise to the concept of impulse and impulsive forces. And if you haven't yet subscribed to Safi Max, kindly support the channel by pressing the subscribe button, and also hit the like button in the video. Thanks for watching.